Okay, thank you very much. Thank you very much to the organizers for setting up this conference and then closing program and for inviting me to participate in all of it. So what I will talk about today is something which was originally motivated by an attempt to understand some defect versions of the ADS-CFT correspondence, but which turned out to have close connections to statistical physics and to condensed matter physics. So more precisely, what I will be looking at today are certain domain walls in a specific quantum field theory, which is of relevance for ADS-CFT, namely ABJM theory. And these domain walls, they are walls which separate regions of space-time where the theory is in different vacua. What I would like to argue is that these domain walls, they constitute integrable boundary states, which means that they do not spoil the integrability of the underlying ADS-CFT system. It's well known there is an integrable spin chain underlying ADS-CFT, and these boundary conditions do not spoil that integrability. And that means that we have access to a lot of exact results about the correlation functions of this defect ADS-CFT system. So more precisely, what I will report on is done in collaboration with Thomas Gomborg, Ding-Long Wu, Konstantin Zarembo, and Dennis Müller. But I should say that the C for all of this was basically in some older papers that I did, other people with Marius Deleuve, who's also here today. Okay. Yeah, so as I said, all what I will be talking about will take place within the ADS-CFT correspondence. And that correspondence, it's a framework which relates a quantum field theory in a lower dimension to a string theory in 10 dimensions. And it's a framework which comes with a lot of symmetries. It has conformal symmetry, it has supersymmetry, and it has a third kind of symmetry, namely integrability, at least in the planar limit. And there are two main examples where this integrability is very well understood. There's the 4-dimensional one, which involves n=4 super-Yang-Mills theory, and a 3-dimensional version, which involves ABJM theory. And it's the 3-dimensional ABJM theory that I will be speaking about today. But I will not be interested in, so to say, the pure ADS-CFT correspondence. I will be interested in a version where we introduce a domain wall in the field theory side, which corresponds to introducing a probe D-brane on the string theory side. And when we introduce this domain wall or probe brane, then we partially break conformal symmetry because translational invariance is broken. And depending on the precise nature of this domain wall, we can break supersymmetry either partially or completely. And there are, in fact, many motivations for studying these defect versions of ADS-CFT. And here I have listed in blue the ones that originally drove us to start these investigations, and in red some ones which came up as a result of our investigations. So first of all, since by these defects we can break conformal symmetry and supersymmetry in a controlled manner, then it can allow us to gain some insight about the integrability, the interplay between these various types of symmetry, conformal symmetry, supersymmetry, and integrability. It also allows us to test the ADS-CFT dictionary in cases where supersymmetry is partially or completely broken. And let me say already from the beginning that all the tests have come out positive. Another motivation is that the integrability of the system gives us access to new exact results for novel types of correlation functions, such as one-point functions, but not only that, also other types of correlators. And our hope was originally that we would produce some useful input data for the boundary conformal bootstrap program, and that's also one of the things we can maybe discuss here. But then it actually turned out that our investigations, they had interesting connections to statistical physics at some level, also quantum information theory, because these domain walls or boundary states that were introduced, they can be described as matrix product states, which is something which belongs to the vocabulary of quantum information theory. And it turns out that the quantities that we actually compute, which are some overlaps, they are of relevance when you study quantum quenches in statistical mechanics. Then you use these overlaps as input for your computations of time development of after quantum quench. What has also happened is that we have got some novel characterization of the concept of an integrable boundary state at the discrete level, something which was well understood in the continuum. And we found novel examples of these discrete integrable boundary states. Finally, we have discovered, or we have exploited, some microscopic duality relations for correlation functions, which have nothing to do with the usual duality relations of ADS CFT, but it has to do with the underlying symmetries. And it turns out that these duality relations, they have very strong predictive and constraining power for correlation functions. And as an example, I will show you how we can use these dualities to find overlap functions in the full field theory, just from the knowledge of overlap functions in a small subset of. So this is the plan of my talk. First, I will explain how the computation of certain correlation functions in ADS DCFT, ADS CFT with a defect, can be expressed as some overlaps of spin chain wave functions. Then I will turn to the concrete setup that I will consider, namely that of domain walls in ABJM theory, and present to you some novel exact overlap formulas for this theory. And as I just mentioned, I will also explain how we can predict new overlap formulas from these microscopic, so to say, duality relations. And finally, something about future directions. Okay. Yes, so first of all, the ADS CFT comes with a dictionary, as we all know, that relates the conformal operators in the field theory to the string states in the string theory. And we have also learned that these objects, both of them, are to be identified as the eigenstate of an integrable superspin chain. So this is pure ADS CFT. But now I want to introduce a co-dimension 1 defect in the field theory at domain wall. And that corresponds on the string theory side, as I said, to introducing a certain probe brain, which is called a Kac-Randall probe brain. In the spin chain language, the introduction of this defect, it corresponds to introducing a boundary state, or it can be described in terms of a boundary state. And by taking the overlap between that boundary state and the spin chain eigenstate, I find the one-point function of the corresponding conformal operator. And this type of computation actually can be done in various versions. There's also an example where the boundary state represents a pair of determinant operators in the field theory, which corresponds to an object known as a giant graviton in the string theory. And there, the boundary state represents this pair of the determinant operators, and the overlap between the boundary state and the spin chain eigenstate is a 3-point function between these two determinant operators and a single trace operator. So that's the same idea. Okay, so now I would like to discuss whether these type of boundary states can be integrable and what I mean about that. So first of all, we know a lot about what it means to be integrable for a boundary state in a continuum field theory. That was understood in the 90s by the Seidmologikovs. So what we need is that there's no particle production or annihilation at the boundary. We need to have pure reflection. Excitations, they can change the sign of the momenta only, and then possibly they can also exchange some external quantum numbers. And on top of that, we need that the Young-Baxter relation should be fulfilled, which means that the order in which reflections appear does not matter. It doesn't matter if this particle is reflected from the wall before or after it scatters with this other particle. And another way of saying that is to say that reflection should be compatible with the bulk scattering. And that is something which is encoded in the boundary Young-Baxter equations. Now this is the field theory language. And then instead of considering a boundary in space, you could also consider a boundary in time by a weak rotation. And that would give you, instead of boundary in space would give you an initial state. And if you translate these conditions to the initial state language, then it means that your initial state has to be built, be a superposition of pairs of excitations with momentum plus or minus p. So that's a simple translation, but it was only realized after we started these studies. And that can be easily expressed in the spin chain language. We simply have to have that all the odd charges, conserved charges of the spin chain, annihilates the boundary states. That's exactly this condition, that you only have excitation pairs with momentum plus or minus p, because all these charges are odd in momentum. Then on top of that, you also need to have some kind of boundary Young-Baxter equation for states fulfilled. But it turns out that this is, it appears to be enough that this condition with the charges is fulfilled. All the cases where that is fulfilled have turned out also to have a Baxter Young-Baxter equation being fulfilled. Okay. Yeah, so here are some examples of boundary states of irrelevance for ADS CFT, which have been found to be integrable. So first of all, I'm talking about a boundary state of the underlying integrable spin chain. And in general, a state of a spin chain would give just by giving the configuration of the spins along the chain like this. And then we have some Hamiltonian and we have some eigenstate, which would be the eigen equation. And a boundary state is simply some spin chain states expressed in the same way, but it's of course not an eigenstate or a simple linear combination of eigenstates. And it is, as I said, integrable if it's annihilated by all the odd charges of the spin chain. And if it is, we expect this integrability to manifest itself in this overlap here being computable in closed form. And here are some examples of boundary states which have relevance for ADS CFT and which have been found to be integrable. So first of all, there are some matrix product states. They are states where you take a sum over all configurations of the spin chain. Each spin at a given site, each configuration of the spin has a certain matrix associated to it. And then you take a linear combination where you trace over the similar combination of matrices as combination of spins in the state. Okay, so one has found examples of integrable boundary states of this type. Another type is valence bond states. Valence bond states, they are also known as two-side product states. They are direct products of two-side states along the chain. And more recently, there have also been identified some cross-cap states where the name is inherited from two-dimensional quantum field theories. The simplest type of a cross-cap state is, if you consider the Heisenberg spin chain, for instance, then a cross-cap state is formed in this way here, where you combine or entangle a spin at a certain side with a spin at a diametrically opposite side. And these have also been found to be integrable, and there are several versions of them which have been found. Okay. And then, as I said, the integrability of these states, they manifest itself in the overlap being computable in closed form. So let me say a bit about what one can say about overlap formulas on general grounds. So first of all, there is an important selection rule, namely that the overlap with a boundary state is non-zero only if the beta roots that you use in the solution of the spin chain by beta ansatz, that they are paired in plus-minus pairs. This is something you prove by sandwiching all the odd charges in between these two states here. Okay, so when that criterion is fulfilled, which corresponds to the field theory operator being parity invariant, then you have a non-vanishing overlap. And it turns out that these overlap formulas, they always consist of the same ingredients. So there are three types of ingredients. So the most complicated or involved overlap formula we have for the matrix product states. There's, well, in all these states that I mentioned, there there's an object which is what is known as a super determinant of the Godin matrix. So the Godin matrix is a matrix which encodes the norm of the beta eigenstate. It's expressed in terms of all the beta groups. And when the beta groups are paired, it factorizes like this, and you can define a super determinant. This super actually refers to this set 2 parity invariance that I mentioned up here. So that determinant always appears, and that's something which does not really depend on the boundary state. It's expressible only in terms of the beta groups. So it's something universal, which is always there. Then for the matrix product state, this super determinant is multiplied by some combination of fused transfer matrices. That is, transfer matrices where the auxiliary space is in some higher representation. And those fused transfer matrices, there's something which can be expressed as sums of ratios of Baxter polynomials, where the Baxter polynomials are polynomials which have the beta groups, beta rapidities as groups. Okay. Then the valence bond states, which were these two-side product states, they're somewhat simpler. They don't have any sums involved. They just have ratios of Baxter polynomials. And in some sense, these valence bond states are more fundamental. They can be used as a starting point if you want to prove overlap formulas for the matrix product states. And yes, as I said, recently one has also started considering cross-cap states. And these are some, to say, the most simple because they have no Baxter polynomials at all involved, simply expressed in terms of the super Godin determinant, which is a bit surprising. Okay. Now I want to go concretely to ABJM theory. What I said so far was some general statements about integrable boundary states and their overlap formulas. Okay, so first, ABJM theory is this three-dimensional quantum field theory, which enters a particular version of ADS-CFT. It's dual to type 2A strings on ADS4 times CP3, and it has n equals 6 supersymmetry. So you don't need to know the details, but it's just some basic facts that I need. It has a field content which consists of 2 gauge fields for wild fermions and for the complex scalars. It's a gauge theory where the 2 gauge fields, they have Chern-Simons interactions with levels k and minus k, and the gauge symmetry is un times un. And like n equals 4 super young Mills, it has a Hoof limit, and here it consists in sending n and k to infinity and keeping the ratio fixed. And it's also a close cousin of n equals 4 super young Mills in the sense that it's integrable in the planar limit. And there's a integrable spin chain underlying the spectrum of the theory. And more precisely, its Lagrangian looks like this. And what I will be interested in is mainly the complex scalars. So you should just notice that they have some interaction potential, which is sextic in the fields. Okay. And as I said, in this theory, I want to introduce a domain wall. So it's a wall which separates 2 regions of space-time where the theory is in different vacua. More precisely, it has different gauge symmetries. So we're in 3 dimensions, so we have one coordinate perpendicular to the defect, and on one side of the defect, we will have gauge group un minus q plus 1 times un minus q, whereas on the other side we have gauge group un times un. Or more precisely, we'll have this gauge symmetry when x2 here goes to infinity, whereas for finite values of x2, the gauge group symmetry will be broken to the same as over here, so there's a match in the defect. And the way the gauge symmetry is broken is by a sum of the scalar fields taking a vacuum expectation value different from 0. More precisely, 2 of the fields have to have a vacuum expectation value different from 0. And all this particular form of the breaking of the gauge symmetry is, of course, something which is dictated by the Lagrangian of the theory. So on this side of the defect, all the fields have 0 width. And I should also say that the width will depend on the distance to the defect. Okay, so how do I find such a possible solution? Well, I have to look at the classical equations of motion for the fields. So it's of course rather involved because the interaction was sextic. So the classical equation of motion for the scalars are quintic. And even if I assume that everything has left 0 except for y1 and y2, then I'm left with some quintic equations of motion. I also assume that all vefs depend only on the distance from the defect, as I said. And that's of course because I want to end up with a defect conformal field theory. But there is a nice way to solve these equations. Namely, there's something called the Passo-Harvey equations, which ensure that the solution conserves half of the supersymmetries. And that equation is linear and only cubic in the fields. And if you plug that solution into the classical equation of motions, then you automatically get the solution. And that's very analogous to the situation that one has in n equals 4 Surya-Mills. There one has a cubic equation of motion, but there are the norm equations which ensure supersymmetry. And if you assume a solution of the norm equations, you automatically get a solution of the classical equations of motion. So the idea is the same here. So I can simply find such a solution, and a solution was found by Terashima in 2008. And it looks like this. As I said, there are vacuum expectation values different from 0 for 2 of the Y fields. And these vacuum expectation values take a particular form, which I give down here. So I do not need to, I can put the vacuum expectation value matrix in the upper left-hand corner. I don't need to take the value to be non-vanishing in the full n by n matrix. So the Y's are in the bifundamental representation. So I have an n by n matrix, but then in the corner I can put some smaller matrix here. And it can take a size of the type q minus 1 times q. So it's not quadratic, but rectangular. That's a concrete solution, which was found, as I said, by Terashima in 2008. So there's one parameter in the solution, this q, the size of the non-vanishing part of the matrix, and I can take it as the value I like, and this is like an n, of course. Okay. Yeah, so now I have my defect quantum field theory, and in that defect quantum field theory, which is actually a defect CFT, and you should notice that the vacuum expectation values depend on the distance from the defect. That's 1 over square root of x2, and that's what is needed to give you a defect CFT. So in this defect CFT, I can have non-vanishing one-point functions, which are bound to take this form here, where x2 is the distance from the defect, and c is some constant structure function that we have to compute. And of course, due to the depth, the scalar operators of my field theory, they can have a non-vanishing one-point function already at tree level. And to find it, I have to take the vefs and insert into my good conformal operators. And now, to get a good conformal operator, I should first of all take alternating sequences of Y fields, because they're in the bifundamental representation of the gauge group. And then I should also take a trace. And moreover, I have to take a good, somewhat complicated linear combination of traces to get a good conformal operator. And it was understood which linear combination by Mina, Henderson, Rambo. Namely, it had to be a combination which corresponds to the eigenstate of an integrable SU4 spin chain, which is alternating, meaning that it has a fundamental representation on, say, the odd sides and the anti-fundamental on the even side. So this is how we identify our operators with spin chain, the spin chain states. And the Hamiltonian is something concrete. It looks like this. Okay. So now to compute my one-point functions, I should simply insert my classical fields into my operators. And this is where matrix product states come into the game, because there's a nice way of formulating this computation using matrix product states. So there are two possible choices for the matrix product state. Here's one of them. I take a sum, as I said before, over all spin chain configurations, and each configuration is weighted with a trace over representation matrices which are combined into SS stagger, SS stagger, like the spins are also in the alternating representations. And with such a state, I can formulate the computation of a one-point function as being equivalent to taking the overlap between a beta eigenstate and this matrix product state, which is just a special spin chain state. Because what this overlap does is that it picks out the combination inside this beta eigenstate, which is the same combination as I have here, and then it replaces that combination with the trace of the corresponding representation matrices, and that is what I need to do to compute the one-point function. And I can do it in two different ways. I can take trace SS stagger or trace S stagger S. And depending on which order I combine SS stagger in, I get a matrix product state with one dimension Q minus 1 or a matrix product state with one dimension Q. Okay. But now I call these S matrices representation matrices because they are actually closely related to SU2 representations. They are actually the square roots of SU2 representation matrices. And to see that, one starts by taking a combination of two Y fields with non-vanishing webs. So alpha and beta here, it should be 1 or 2. Then you get 4 objects here, phi, alpha, beta, and it's natural to expand them in Pauli matrices and the identity like this. And you can put use a condition that these Y's fulfill these Passo Harvey equations and revise this as an equation for the complex combinations Y dagger. And if you do that, you find exactly that the norm equations come out again. The norm equations that we know from N equals 4 super young mills for 3 of the fields, and the last field here fulfills a somewhat simpler equation. But this is how you see that this product of fields Y dagger is actually given in terms of a SU2 representation matrix. And the field phi here is just something which is proportional to the identity with a proportionality factor which depends on Q. Okay. So now if we go back, then instead of inserting the S matrices, I can of course just insert these SU2 representation matrices in my one-point function and compute. And you see there's a simplest case, which is Q equal to 2. In that case, I get a matrix product state of one dimension 1, and the matrices along the chain are proportional to a delta function, so it exactly gives me a two-side product state where I have to identify neighboring states. So the matrix product state for point dimension 1 is actually what I denoted earlier as a balanced bond state. Okay, now you can repeat this exercise with the Y's in the opposite order, and then you will get this combination of Y fields related to a Q dimensional representation of SU2 instead of a Q minus 1 dimensional representation. Okay. Yeah, so now let me start by showing you what the overlaps look like for the simplest case of Q equals 2. So in my spin chain formulation, I first have to choose a vacuum of the spin chain. So I choose a vacuum which corresponds to the operator trace Y1, Y2 to the 2 dagger to the power L. That's an operator which does not get any anomalous dimension, and therefore it corresponds to 0 energy in the spin chain language. On top of that state, I can then have excited states, which are described by a series of beta roots. There are 3 types of roots for this alternating SU4 spin chain, and they are associated with the 3 nodes of the thinking diagram of SU4. And now one can easily derive some selection rules for this overlap that I mentioned to be non-vanishing. If you just look at the properties of these S matrices, you find that the number of roots at the 3 points have to be equal and to be equal to the length of the spin chain. Then there's also this Z2 symmetry that I mentioned earlier, but due to the particular nature of the boundary state in this case, then it is a Z2 symmetry which combines the roots at the middle node with themselves and the roots at the 2 exterior nodes with each other. And that is something which is called an achiral boundary state. And once you've set all this problem, it actually appears that this type of overlap, it has been studied before in the statistical physics community by Thomas Gumbor, who actually found exact overlap formulas for these alternating spin chains. So we can read off the result from there. And we get an expression for the overlap, which is in accordance with this general formula that I explained in the beginning. It's quite curious because it involves only the Baxter polynomial at the middle node here. And it involves it 4 times, so to say, 2 times under the square root, and okay, 1 time outside, counting the segments 2 inside. And we represent it in this way here, where we put for each node of the Dynkin diagram, we put the argument of the Q function in the formula, measured in with the arguments in integer. The integer counts the number of I over 2's in the argument of the Q function. So this is a compact notation for the. And this is what, the result is for the simplest case of Q equals 2. So it encodes all the one-point functions of the field theory, any type of operator. Okay. But then the next question is, of course, what happens if we go to a higher bond dimension, if we don't consider Q equals 2, but some higher version of Q, or some higher value of Q. And that question can also be answered. There is actually a recursive strategy for deriving such overlap formulas, which were proposed by Barnard and Gumbor. And it's a recursive strategy which is based on the nested coordinate basic ansatz. And this is what the result of that strategy looks like. So this is, of course, for general Q. And if I set Q equals to 2, which is what I had before, then everything in the first line trivializes to a 1, and the sum contains only 1 term, and then I recover my formula from before. But for general Q, then I get this dressing by some kind of fused transfer matrix. And the way in which one proves it is to start from the matrix product state, which involves some traces. You cut it open to a general matrix state, and then you simply compute the overlap for all the diagonal elements. But under the assumption that each of these diagonal overlaps is factorized into reflection factors. And the relevant reflection factor you find recursively, you start by computing the full reflection matrix of the entire spin chain, and then you relate that to the reflection matrix of SU2 via the nesting procedure, and that allows you to find the overlap in a closed form. And then in the end, it's useful to check numerically because there are some assumptions on the way. For instance, this here implies an assumption that the matrix product state, it factorizes into suicide product states at all levels in the nesting, otherwise it would not work. But anyway, it has been checked numerically in this formula, and it works. Okay, but this is only for the scalar sector of the theory. The theory, of course, also has fermions and gauge fields, and the question is, can we extend this formula to the entire theory? And the answer is that this is where these microscopic duality relations come in that I spoke about before. Because we know from, we have the experience from N=4 super Young-Mills that this overlap formula for the valence bond states, it's singled out by having a very nice property of transforming what we call the covariantly under Thermionic duality transformations. So we want to, and we also learned for N=4 super Young-Mills that if you just know the overlap for the scalar sector, then by requiring these duality relations to fulfill, then you can conclude what is the overlap for the full theory. And now we want to see if this works for ABJM theory. And what are these duality relations? Well, it's something which is encoded in what is known as a QQ system for the spin chain, which again is nothing but the fact that you can write the beta equations in many different ways. Because you can choose what is the vacuum of the spin chain in many different ways, what is the first excitation in many different ways, what is the second, and so on. And all that is included in the QQ system. And for N=4 super Young-Mills theory, there are a total of 2 to the 8 different Q systems, which are connected via a web of dualities, which form a Hasse diagram, which looks something like this. So the QQ system is not as well understood for ABJM theory, but the Thermionic dualities that we need are fine. So these dualities, they can be, they are the relation between the various Q functions. They can be split into Thermionic dualities and bosonic dualities. And the Thermionic dualities, they correspond to changing the Dynkin diagram underlying the spin chain description of the theory. Because for a super symmetric spin chain, there are different choices for the Dynkin diagram. A super Lie algebra has several possible Dynkin diagrams. And now dualities sounds very fancy, but it's nothing but a change of variables in the beta equations. You take some Q function and you replace it by some other Q function, Q tilde. And then the beta equations change, but they have the same content, of course. And also all my one-point functions are, of course, the same, no matter which beta equations I find to determine them. It's some property of the quantum field theory, but it can be expressed in different ways in the different, using the different parameters to solve the beta equations. Okay. So what are these Thermionic dualities in general? Well, there are changes of variables, which, as I said, they allow you to move between the beta equations corresponding to different Dynkin diagrams of the super Lie algebra underlying my theory. And here's an example of a change of variable, which is a Thermionic duality. You replace a Q function at the node A of the Dynkin diagram by a Q function QA tilde via some relation like this, where these pluses as minuses means that the argument has been shifted by plus and minus I over 2. So a Thermionic duality involves only a Thermionic nodes and its two neighbors. And what it does effectively in terms of beta equations is to change the nature of the neighboring nodes from Thermionic to bosonic or vice versa, depending on the starting point. And then it changes the signs of the off-diagonal elements in the Cartan matrix. And from the Cartan matrix, you write down the beta equation, so it changes effectively the form of the beta equations. Then one also has to worry what happens if the node that you dualize after is one that carries momentum or non-vanishing Dynkin label. And if it doesn't carry any Dynkin label, then nothing happens to the Dynkin label anywhere. If it does carry a Dynkin label, then the Dynkin labels change on the neighboring nodes. Okay, but what the interesting part here is how do the various parts of the overlap formula change? Of course, Q functions is obvious, the change as we defined. Well, we change one Q function to another Q function, but what happens to the super determinant of the Godin matrix? Because the Godin matrix cannot be expressed in terms of Q functions. But it turns out that it has a very nice transformation property under these Thermionic duality transformations. So here I have written D and D tilde as the Godin super determinant before and after the transformation of variables. So you see that that if my transformation, my overlap formula depends on a Q function QA by it being multiplied to D with argument 0, or being divided or dividing D with Q with argument 0, then my overlap formula preserves its form. It's again expressed in terms of Q functions, but now Q functions at the neighboring nodes. And this relation here is something that we have found numerically. But once you think that an analytical proof would exist, because this is a statement about determinants and polynomials, and it's a simple linear relation. But an analytical proof is wanted, and anybody can have a try. But the nice thing is that overlap formulas which involve this combination of the super determinant with a back polynomial, they transform covariantly. I mean, they will keep their form. So here is the overlap formula symbolically. Either you start with a Q of 0 in the numerator, then it moves under the duality transformation to the denominator, and then there's an additional couple of Q functions in the neighboring points, or you start with it in the denominator, move to the numerator, and divided by some Q functions at neighboring points. And now it turns out that if we require our overlap formula to be covariant under this type of duality transformation, then we actually fix it completely from just knowing a small part of it. Okay, so these are the possible thinking diagrams for the super Lie algebra, which characterizes the symmetry of ABJM theory. This one is the simplest one. And my scalar sector that I consider corresponds to the SU4 thinking diagram, which is this lower part here. But I can also equally well use this other thinking diagram to describe my symmetry. And I can get from one to the other by fermionic duality transformation. Here I make the duality transformation after this single fermionic node. In the second step, I make a duality transformation after this node. And finally, I can make a duality transformation after this fermionic node. And as I say, I wanted to determine my overlap formula by requiring the overlap to be covariant under these dualities. And I then need a few assumptions, but they're not very severe. First of all, I assume that my duality formula is factorized, that it only involves some, again, the Bourdain super determinant, and then a ratio of the Baxter polynomials in front. And here, this product is a product over nodes of the thinking diagram. And these other two products, it just signifies that I can have a number of Q functions associated with that node, either in the numerator and denominator, and with various arguments, which are integer multiples of I over 2. And then I need also to know how the super Bourdain determinant transforms. And I need a generalization of the formula that I had of the previous slide, because here I can have more than 2 neighbors of a given fermionic node. But it turns out that at least numerically, the formula generalizes easily. Now, instead of having a product over 2 neighboring nodes, I just have a product over all neighboring nodes. So it's the same type of transformation formula. And again, it would be nice to have a proof, but we don't have it. And just knowing the overlap in this SU4 subsector of the theory with what I found, it turns out that if I want this to transform covariance under fermionic dualities, then there's only one choice for what to have on the other nodes. Well, this was because I needed to have either a Q function at 0, either in the numerator or in the denominator everywhere. Yeah, I don't go into the details of describing it, but you can check for yourself. There are no other possibilities than this. There is a new feature compared to n equals 4 super young Mills, that at some point you get a difference between 2 terms. But that's because we have this double product of 2's here, which are not transformed by the duality transformation formula, which only involves 1s and 0s. So therefore, you have to use the QQ relations to get rid of this old QQ function here. And that leads to this relation down here. Okay. Yeah, that was the main result of my talk today, that we can actually fix the overlap formula for the full ABJM theory, just starting from the overlap formula for the SU4 subsector, which is an overlap formula which is derived analytically. Okay, and what's left to do? Well, it would maybe, of course, be nice to check that this overlap formula that we found by fermionic duality is actually true, which would require a field theory computation. But it is consistent with everything we know so far. It would, of course, also be nice to have a proof of the duality transformation formula, which, as I said, requires nothing but a manipulation of determinants and polynomials. Then it could be interesting to try and bootstrap the formula to higher loops. This has actually been done for n equals 4 super young Mills theory, where you have an asymptotic formula for these overlaps for all operators in the theory. And that formula, being only asymptotic, of course, also asks for a finite size correction formula, some kind of TVA for these overlaps. That's something which has not been done. And one can wonder about whether there are other integrable defect setups hidden in AJ-CFT, such as the Coulomb branch of n equals 4 super young Mills, defects of other codimensions, or defects in the lower dimensional versions of ADS-CFT that I know that many people here are are interested in. So that's all. Thank you.
Thank you for the very nice talk. So I have a question regarding one of your points in the outlook, which is the going towards the finite volume through some TBA or something like that. So I've not been following this very closely, but there is a quantum spectral curve for this ABJM, and that is written in terms of essentially QQ relation for quantum Q functions. And I was wondering whether what you have shown us can inspire some maybe natural guess of what you could do in terms of these quantum spectral curve variables, and also what perturbative calculations are available to test this type of guess.
Let's start by the last point. The perturbative program has not been set up yet. It was set up for N-4 super Mills. It's quite intensive. You have to expand your fields around these vacuum expectation values, but they are matrix forms of the couple, different flavors and different components of the fields. So that's a rather big project in itself, but I'm sure it can be done. It was done for N-4 super Mills, where you had to use quasi-spherical harmonics and so on, and use the SU2 symmetries again and again. It can be done, and I think it needs to be done if you want to bootstrap it to higher order and make sure that it's correct. It's something on the bucket list. And of course, yeah, the quantum spectral curves should be applicable to help us find a finite volume version. Of course, it doesn't help us with the Godin determinant because it's not expressible in terms of Q functions. But there's something called the G function that people use instead that is related to this quantum super determinant. So it has to be worked out. It hasn't been so far.
I might miss this, but so have integral defects been classified for ABJM?
Is the defects have been classified? Or?
The integrable, the ones that preserve integrability?
Not really. We have found this class of integrable matrix product states, and one particular case is a valence bond state. Thomas Gambor has also identified possible cross-cap states for ABJM theory. There are several types which involve all the scalars.
So I guess my question, so at one point you were, the UN times UN gauge group was being broken to UN minus Q, UN minus Q minus 1.
Yes.
That is governed by integrability, or that is?
No, that's governed by the field theory itself.
It
follows from the classical equations of motion.
So there is that is the only choice, or of breaking of the gauge group?
I guess you could try to look for
other class solutions.
Yes. But you want some solution where you just have dependence on the defect, distance from the defect, because you want to end up with a defect CFT in the end to be able to use all the symmetries. But in principle, there could exist other solutions.
Okay, so the solution you showed is one that's been found, but it's not been shown as the only solution.
I don't think it has been proven that is the only solution. You start from, if you require that half of the supersymmetries are preserved, then you need this equation is fulfilled. If you put that into the classical equation of motion, you can show that you have that solution that I showed you. And that's something which was done in 2008 by Terashima, but it's not guaranteed that there are no other solutions.
So for N=4 super Mills, we also had a bunch of string theory results that we could compare to. What's the situation here for ABJM?
Yes, I should have mentioned. I mean, we know what the dual string theory setup looks like. It's a probe D4 brane in the background of a lot of D2 branes. And then this D4 brane has to have a particular geometry, which involves a CP1 over S2. and there has to be a flux there. And for n equals 4 super young males, you can combine the 't Hooft coupling with the flux and make a double scaling parameter. It seems from the string theory side here that you can do the same way. But for the moment, we don't see this double scaling parameter coming out naturally on the field theory side. But it might not be a surprise. N equals 4 super young males has more symmetries than ABJM theory. In ABJM theory, the 3-point functions are, for instance, not protected, and 1-point functions in a defect CFT is somewhat like 3-point functions. So maybe we should not expect to have this match in a double scaling image. And I should also mention that Georgios Lider-Dopoulos has looked at the string theory side to see if you could prove the classical integrability of the string theory on that background, and it works. So classically, the string theory version of the problem is integrable.
I have one very basic question in the beginning of your talk. You mentioned something like integrable boundary state, and MPS is one of them. And what is precisely this integrable boundary state? If, for instance, if you apply Q2n plus 1 and vanishes, then does this state, is it integrable? Or, for instance, I can think of Nair state. Nair state satisfies this criteria, Q2n plus 1. Yeah.
But Nair state is integrable.
Is it integrable?
Yes.
And is it part of MPS, or it's not?
It's a two-side product state. I mean, Nair state is you take a product of two-side states.
In your word, is it like a VBS, or it's a
yeah,
part
it's a VBS.
Oh, okay.
In but in the XX expansion, any two-side product state is integrable, has been shown by Potsky.
So is MPS the most general integral boundary state, or it's not really classified?
I think it's not fully classified. But it would be interesting, of course, if one could give a full classification and show that there is no more.
So let me check. If you satisfy this Q2n plus 1 apply psi 0, is it integrable, or you need more conditions?
In principle, I need the boundary on my equation, but it is proven out to be sufficient in all the cases that I have mentioned.
So how many supersymmetries are preserved by your defect in general?
Should be half.
I see.
Yeah.
So for example, then if you include, well, for example, if you relax that to less supersymmetries, and then you can write the more general equations, more general than Harvey, but more complicated. So
that's very possible that there are other solutions
so
which
you can
are.
write down, yeah, I think I did a similar thing for N equal 4, not for ABJM, but then you can try to classify, write more complicated equations and write solutions, etc. So that's a field theory aspect. And I wonder if there is a, counterpart, analysis for these more general defects. Is there room in integral model side?
I know that for N equals 4 super young males, you can also find the integrable defects which are not supersymmetric. So you could try.
Yeah, for example, let's say quarter VPS, for example, and
yes.
then and then you get some more general, some reduction of self-Young Mills equation.
Yeah, that would be very interesting. I know only one example where there's no supersymmetries conserved, and that is in N equals 4 super young Mills theory, where you have a setup which is dual to a D3, D7 branch system. That in their supersymmetry is completely broken, but still it's integrable, at least at the lowest order in perturbation theory. It has not been proven above that. But,
okay, thank you.
I had a question about this superdeterminant. So its definition is that as the ratio of determinant of G plus over G minus, or the other way around.
yes.
Where G plus and G minus are matrices associated to the boundary problem.
Yes.
So do you have a dependence on the linking diagram also for N equals 4 super young Mills? And do you have the rules of transformation of D?
For n equals 4 supernomials?
N equals 4 supernomials.
Yes.
Yeah.
Yes. It works in the same way. That's where we started from.
Yes.
We first considered for n equals 4 supernomials because the thinking diagram is
Yeah.
just a line.
Yeah.
And
So
there it works beautifully. That we wanted to check that the full formula was consistent with all the small sub-formulas that people had found on the way.
yeah.
And it worked, but we realized that we could actually start from one of the sub-formulas for the scalar sector and move the other way and find the entire the overlap for the entire theory, and that's what we repeated now for ABJM.
Okay, so yeah, it will be very interesting to have a analytic proof of this duality relations.
Yes.
Yeah. Okay, so thank you again for the nice talk. Now we have lunch in the courtyard, and we'll be back after lunch.